Okay, so let's finish up with our final topic in circuits, looking at electric power and efficiency. A pretty straightforward topic, nothing really new or anything. Our power is just defined as work over time, so energy transformed divided by amount of time. So there's another way we can write it. Power is equal to charge times voltage divided by time. This is basically how we derive that PIV. Power is just equal to, if we know current, we know voltage, we know power. We can also rearrange that since we know PIV and VIR, P equals IV and V equals IR. If we do a little bit of substitution, we can create power in terms of I and R, power in terms of V and R, and so on. Efficiency is pretty straightforward as well. Just what do we get out divided by what we put in. Again, there's always wasted energy. Like for example, if we have a light bulb creates light, but it also creates heat. We want the light, we don't want the heat. So the energy, the lumens, the energy we get to produce the light would be our output. Energy input would be the energy, like all that went into getting it, so it would include the heat as well. So let's just scroll down to some examples. Here's two examples to finish off with on this topic. So we have an electric heater draws 15 amps on a 120 volt line. So 120 volt is basically what we get in our homes in Canada. So how much power does it use? And here's a different unit for power, the kilowatt hour. That's right, it's not the power, it's actually kilowatt hour is the unit for energy. Oh, where's my pen? There it is. It's kind of confusing with that one because it has watts. We know watts is power, but it has hour. So you think work as a power is equal to work over time. So work is equal to power times time. So we can see there's our power and time. So when we say kilowatt hour, it's actually the amount of energy used, not power. So be careful with that one. So we have P equals IB. We have 120 volts. So we get 1800 watts. Yeah, so just remember, note, kilowatt hour is energy. And why do we even use that one? Because usually in our households we use so much energy. If we just use like joules, it's going to be a really big number. So they convert to kilowatt hours. So if you ever, when you get older, you own your own house and you get your energy bills, this is what they'll actually measure it in. Okay, so kilowatt hours energy. So therefore, work is equal to 1800 watts. And we're using it for 30 days. And each day we're using it for 3 hours in a day. So the amount of work energy we're using is 162,000 watt hours, which is 162 kilowatt hours. And this is approximate price. I'm not sure what energy. You can actually just look up BC Hydro to see how much they're charging you. It's 12.0 cents per kilowatt hour. Usually what they do is if you use a little bit of energy, they charge you a little bit. So for up to the first amount, you might be getting charged like 11 cents. And if you ever surpass a certain quantity, then they start charging you more, like 12.8 cents. Like, who knows? It's just some value. I'm just going with 12 cents. And we are using 162 kilowatt hours. So what you see is for this electric heater, it's costing us $19.44. You may think that doesn't cost too much, but again, it's not just your heater that's being used. You have lights turned on all the time, your computer that you're using computer or phone or whatever it is you're using to watch this video, all uses energy. Energy is money. Here's another one. Suppose a company decides to ship 150,000 watts over a 2.0 ohm transmission line. Is it more efficient to use a low voltage, 560 volts, or high voltage at 20 volts? What can be said about the relationship between efficiency, voltage, and current? So you may have heard the thing with like loose power lines and danger, stay away. That's because, well, we'll see right now. So let me just scroll down first. So I'm going to solve this twice. Let's put the dotted line down the middle. You know, power is equal to current times voltage. So we want to ship 150,000 watts. And it's saying, is it more efficient to use 560 volt line or a 20,000 volt line? So I times 560. So if we want to do a 560 volt lines, we need a current of 268 amps. So now we can actually solve for how much power is lost. So lost power, because that current is being traveled through this very long line from wherever our power station is, i.e. like the hydro dam, all the way to our homes or whichever other source of energy we're getting from. So that current is passing through the wire. And normally we don't think of wires as resistors, but they are. The wires are using up or consuming energy. So we go P is equal to, so let me just write that down nicely. So it's consumed by the resistor. So in this case, the wire, as it travels from where we're getting our energy from. So P equals I squared R, 268 amps squared, 2.0 ohms. And the reason I'm not actually using 560 volts is because if we think about the power line, like we have our source of energy at some point, right? And then it's going to travel some power line to your home. The voltage here is different than the voltage here, right? So we're losing voltage. If we actually knew the voltage drop across that line, then you can actually use that in our equation, but we don't actually know. So we don't actually know the voltage drop across that wire. We do know how much current is being traveled though, because we used to solve for that. Okay. So there's our 2 ohm transmission line. We get a value of 1.44 times 10 to the 5 watts. So we can actually solve for our efficiency. So we wanted to transfer 150,000 watts, but we lost 144,000 watts in the process. So it's kind of a waste of money. I don't think anyone would agree to this. You got 4.2% efficiency. Oh, pitiful. Let's see what happens if we did the other one, 150,000 watts. I times a 20,000 volt line. You get a current of 7.5 amps. Go P equals I squared R. Same idea. You get 7.5 amps squared times 2.0 ohms. You get 113 watts lost. Pretty good. Efficiency is 150,000 minus our lost energy divided by our input, and we get almost 99.9% efficient. That's why we have things called transformers, which we'll learn about more in the next topic. Transformers are often placed at like where we're getting the energy from to ramp up the voltage, and then it gets back to the city, we're going to ramp it back down to more usable, because we know at our houses we just use 120 volts. In our sockets we had 150 volts ready to go. That would be quite dangerous. So generally speaking, we transmit power with high voltage, low current. Also, that's why it's extremely dangerous to go next to loose power lines. If like there's ever an accident and there's power lines just on the ground, you'd never want to go near them. Huge potential. If you come between that and the ground, huge amounts of current is going to pass through, and you'll most likely die. So when you get to the city, ramp it back. So when we get to your houses, or in the city, we ramp it back down to a usable voltage. Again, this voltage is still very dangerous, but Noise danger is 20,000. Another benefit for a smaller current is we can use a smaller wire. If you have such a huge current, you need a huge wire to contain all those electrons traveling through. Smaller wire, more money. I think there is currently newer technology in I think it's already been developed where they can actually transmit at low voltages as well. Or actually, I think that's to do with DC and AC, which we'll get into next day. But for now, we are done. Circuits.